Okay, the states of matter, and especially talking about the gas laws. So, states of matter is the term we use when we talk about solids, liquids, and gases. Um, we could also go ahead and talk about plasma, called the fourth state of matter beyond gas. But it's really not going to have any relevance for our class because it only exists at extremely high temperatures, such as stars and things, and where basically all the particles have lost their electrons and have become charged. So it's a different state of matter that's not going to hold as much relevance for us. So mainly for us, we're going to think about solids, liquids, and gases. So this page pretty much sums it up. You probably already had a pretty good idea of this. In the solid state, particles have fixed positions. In the liquid state, particles are held close to each other but can move past each other. And in the gas phase, particles are separated from each other and moving about randomly. A couple things to remember is that in the solid state, the particles are not motionless; they are vibrating in those fixed positions, and so they end up having a fixed shape and a fixed volume. When you end up in the liquid state, then you have a fixed volume. The liquid is held together into a certain amount of space, but the shape can change based on the container. And gases will expand to fill their container, so they have neither a fixed shape or volume. And that for any particular substance, as the energy increases, meaning basically as the temperature increases, this is the direction of the phase changes. So you'll go from solid to liquid, and then from liquid to gas. Okay. Before we get into gas law stuff, we need to review our units. Some of these we've already looked at. For temperature, it's going to be really, really important that we always use the unit of Kelvin. And Kelvin gets referred to as the absolute temperature. So in Kelvin, the important thing is that 0 Kelvin, really is the lowest possible temperature, because temperature is the average kinetic energy of particles. So essentially, it's how much are particles moving. And so the lowest temperature is when there's no motion. So theoretically, there is a lowest possible temperature where everything has stopped moving, and we call that absolute zero. So 0 Kelvin is designed to be the absolute lowest temperature possible, so 0. It was designed to match the Celsius scale. So 1 Kelvin, not a degree Kelvin, but 1 Kelvin is the same size unit as 1 degree Celsius. And so changes in temperature are equivalent in kelvins or degrees Celsius. They're just off by 273 degrees. So if it's 0 Kelvin, it's minus 273 Celsius. Whatever the temperature is in Celsius, you add 273 to get to Kelvin. Temperature in Celsius equals temperature in Kelvin equals temperature in Celsius plus 273. Subscript those. So if you have a temperature of 25 degrees Celsius plus 273, that temperature is 298 Kelvin. And those are the same value. Okay, so 298 Kelvin is the same as 25 degrees Celsius. Okay. Whenever you talk about multiples of temperature, so if you talk about a temperature doubling, you have to always do that in Kelvin. And it's because it's that absolute nature that there's no negatives in Kelvin. Because if a gas is at 25, then its temperature is doubled. What is the new temperature? So the process is that you first have to take the Celsius temperature and turn it into Kelvin, 298. Then you can double it, if that's what the question told you to do. So you double that, and that becomes 596 Kelvin. And if you want to put it back into Celsius, you subtract 273 and end up here. So when you double something at 25 degrees Celsius, you actually have to heat it up to 323, not 50. That would be the sort of trap answer on the IB, is that they would probably put an answer here like this. But we would know it's not 50 because that would be done in Celsius, not in Kelvin. So it'd be false. If you do things in the negative, then it makes a lot more sense why you need to do Kelvin. If you have something at negative 10 degrees and you want to double it, doubling negative 10 degrees would get you to 20 degrees Celsius, negative 20 degrees Celsius. And if you think about what temperature means, temperature is the speed of particles, right? if you double something's temperature, you should double the speeds on average, more or less, or at least the average speed. And when you do that to negative values, it actually implies that they're getting slower. So this doesn't make any sense. So the only way to do this is to first convert it into Kelvin, which would be 263, then double it, that would give you 526, and then you could subtract afterwards to turn it back into Celsius if you needed to. When we talk gas laws, it's going to be really important to have certain temperature values that we compare things in, because temperature has a big effect on how gases behave. So if I'm talking about one gas and you're talking about a different gas, you need to make sure we're talking about them at the same temperature if we're going to make sure that what we're talking about is comparable. So sometimes things will be talked about as being at STP, which means standard temperature and pressure. So this is the STP one. Standard temperature is 273 Kelvin, which is the same as 0 degrees Celsius. Standard ambient temperature is more like room temperature, and this is sometimes referred to as standard ambient temperature and pressure. And these values are listed in the data booklet in table 2, I believe. But standard ambient temperature is 298, which is sort of a warm room temperature. But these are both temperatures that get used to sort of standardize how we compare gases. For pressure, the SI unit is the Pascal. It's based on the SI units of force and area. It's a pretty small unit of pressure, so this pressure, which is 100,000 pascals, is normal atmospheric pressure at sea level. It's kind of a mouthful to use all the time, so the most useful value that we use is the kilopascal. So a kilo means 1,000, and so standard pressure in kilopascals is 100, and that's a nice round number for us. So in both of these things, we talked about standard temperature and pressure, or standard ambient temperature and pressure. 100 kilopascals will be the value that we use for either of those things. For volume, we're going to mostly use the dm cubed, which is essentially the same as a liter. 1 cm cubed is a milliliter. 1 dm cubed is a liter. Okay, so it's very important that you get familiar with using dm cubed and cm cubed, because that's what the IB will show you. And the last value that we're going to care about with gas laws is the amount of the gas, and so that's the moles of gas particles. Okay, the changes of state, you probably have heard these before. Going from solid to liquid is melting. Going from liquid to gas is called vaporization. There's different ways a liquid can go to a gas. It can evaporate, which is when it does, it goes to liquid to gas at the surface. And there's also boiling, which is when it goes to liquid to gas beneath the surface. In reverse, you've got gases can condense back into liquids, and liquids can freeze into solids. You also have some other phase changes, such as sublimation, going from solids straight to gas, and deposition, going from gas straight to solid. And those do occur for certain substances under certain conditions. If we're thinking about temperature changes during changes of state, it's pretty interesting that when you have a solid, you can warm a solid up. But then if you start to melt a solid, the temperature of that melting solid actually will plateau during the phase change. And then once it's all liquid, it will warm up again until it begins to boil. And then the temperature will stay constant, and then the temperature will rise. And so it's pretty neat that they actually will follow the different phase changes. So up here we have gas, up here we have plateau is boiling, and the temperature we would call the boiling point. But let me take that away so that we have room. This is when it's liquid, warming up. This plateau down here would be melting, and down here we would have a solid. Okay. So solid, melting, liquid, boiling, gas. And those plateaus would be exactly the same if we did the reverse. So if we were cooling a gas down, it would start warm, and it would plateau at the same temperature. You could cool a liquid, and it would plateau as it froze, and then you could make the solid colder. So again, just to add in some notes, this plateau right here, this is known as the melting or the freezing point. They are the same value. So for water, that's 0 degrees Celsius. And here you have the boiling point at standard pressure. So why does the temperature plateau? Well, it turns out that during those phase changes, the energy that you're putting in or taking out of the substance is not going to how fast the particles are moving, which is what temperature is a measure of. The energy you're putting in is going to the stored energy of the particles, their potential energy. It makes sense if you're putting in energy, we know that energy can't just disappear. So if it's not making the temperature go up, which is the kinetic energy, it must be going someplace else. So it's going to a stored kind of energy. And in chemistry, you can think of that we have a special term for stored energy or potential energy, and that's enthalpy. So that's what enthalpy means. And so over time, we could do the similar type of graph that if we're looking at the same times, a solid has X amount of potential energy. And then as it becomes a liquid, its amount of potential energy increases. That's why there's no temperature change. All of the energy during the melting is going into the potential energy of that substance. Then when it's a liquid, it plateaus. And then as it becomes a gas, it gets a lot more potential energy until it's a gas. And sorry about that. Second, it should be flat. Okay. So these represent, instead of kinetic energy, now we're talking about potential energy. So this is gas. This is vaporizing. This is liquid. This is melting. And this is solid. So phase changes result in changes in stored energy, which we call enthalpy. And if you increase something's stored energy, its enthalpy, that process is called endothermic. So what I've just shown here, melting and vaporizing and also sublimation are what we call endothermic processes because heat, thermal energy, is going into the process, into the substance. And so we'll make that green as well. So these phase changes, the vaporizing and the melting, those are endothermic processes. In order to make something go from gas to liquid and liquid to solid, those are going to be exothermic. So I lost my marker here. There we go. So something starts off as a gas, but as it condenses, it loses energy. And so it releases energy to the surroundings. And then it's a liquid. And then as it freezes, it loses energy to the surroundings. And then it's a solid. So the other phase changes, going in the reverse direction, are the exothermic phase changes. Exothermic would be condensation and freezing, and also deposition. These are terms that get used a lot throughout the course, so I'm going to keep using them. Exothermic is releasing heat energy, and endothermic means absorbing heat energy. Boiling, it turns out, is a little more complicated than the other phase changes. Boiling actually depends on pressure. And so when we talk about water having a boiling point of 100, that's only true when water is at normal pressure. So when the pressure is pushing down on it. And so liquids have this property known as vapor pressure that changes with temperature. So technically, the boiling point is equals the temp where the vapor pressure of a substance equals the atmospheric pressure. It's really more complicated than you're going to need to know for the SL syllabus, but it implies that it's a little more complex than something always boils at a given temperature. If you look at the dark blue curve for water, you can see that it can boil actually at higher temperatures than 100 if the pressure is higher. And that's the basis behind a pressure cooker that some people may have in their kitchens. If you seal up the container, you can create greater pressure and therefore make the water get hotter. Otherwise, on the stove, water should only get to 100 degrees Celsius and then it can't get any hotter, it starts to boil. If you go up on a mountain, very, very tall mountains where you're at high altitude and the pressure is lower, then water will actually start boiling below 100 degrees Celsius, so it doesn't get as hot. It actually makes it difficult to cook things quickly because the water is not as hot. And lastly, before we get into specific gas laws, we're going to talk about gas particles and just a reminder of some of the things that we're going to assume about their behavior. So this is sometimes referred to as the kinetic molecular theory also, some of the things we're going to say here. Really, we're assuming some things about ideal gas behavior. Real gases aren't going to necessarily act exactly like this. And some of these things we're going to talk about are from kinetic molecular theory, which is kind of what we were talking about here, how particles always have some kinetic energy and some motion, and it increases as we go from solid to liquid to gas. And now we're going to talk about kinetic molecular theory as it applies to the gas phase. So when we talk about a gas, we're going to assume that gas particles themselves take up negligible volume. So they basically have no volume when compared to the overall volume of the gas. So gases are mostly empty space. So what we mean by that is when you have a balloon of a gas, this is the balloon, that it takes up, let's say, 1 liter of volume, but the gas particles themselves are so tiny, even tinier than these dots represent, so much tinier than that, and they're so far apart that most of what's in the balloon is empty space. So we assume that the little particles of gas, we don't really count them as having any volume. Again, that's not really true. That's a sort of simplification of how gases really act. So that's why we call it ideal behavior. We sort of pretend that the particles have no volume. Gas particles experience no attractions for other gas particles, which leads to elastic collisions. So when they bump into each other, they bump and they don't lose any energy. Really, net, the energy is all conserved in their motion, and they bounce off. So the assumption is that the gas particles have no attractions for other gas particles. That's not true, but at most temperatures for gases we're familiar with, the particles are moving so quickly that the attractions they have don't really get any time to actually interact. And so when gas particles collide, more or less, it's sort of a safe assumption that they just kind of bounce off each other and their attractions don't play too much of a role. We assume that gas particles move in straight line motion. So they are moving in one direction until they hit something else, and then they bounce off in another straight line until they hit something else, and then they're going to bounce off in another straight line. So we kind of think of them as like, balls just being bounced around off each other, and they're moving really fast, and they collide with one another all the time. But each like individual bit of motion is straight line. And lastly, a gas particle's average kinetic energy, its speed, more or less, is proportional to its absolute temperature, or its temperature in Kelvin. So we could have a graph like this that basically says that temperature means kinetic energy for particles. So remember to recognize that when the temperature of something goes up, that means the kinetic energy of the particles is going up on average. And that means that the particles are moving faster on average. So speed, sorry, it's hard to write this with the little marker. I should have used text. Okay, and the last thing for this video, this comes much later on in the syllabus. It's part of topic 6, kinetics, but related to how temperature affects particle speeds. It's called the Maxwell-Boltzmann distribution. And if you look at just one at first, this dark blue one, the idea is that when you're at a particular temperature, not every particle is moving at the exact same speed. So notice the left says number of molecules, the bottom says kinetic energy. So it's kind of like a bell curve. 300 Kelvin is 27 degrees Celsius, so a warm room. Most of the particles are moving about this fast. They're moving with a certain amount of kinetic energy. The graph shows that there are a few particles that are moving really slow with very low kinetic energy, and there are some particles that are moving quite fast because of the way they're bouncing around. But overall, there's an average speed or an average amount of kinetic energy. And as you increase the temperature, which is represented by going to the right on this graph, you can see that more and more of the particles are moving down here towards the right. They're moving with more and more kinetic energy. But it doesn't mean that every particle, when you heat something up, all of a sudden moves faster. There's still particles that are moving quite slow down here, and there's particles down here that are moving really, really fast. What's important is that the average, which is kind of like the peak of the curve, right? The average has increased when we increase the temperature. And again, it happens even more if you go to 500, right? The average, sort of the peak of this bell curve, is further to the right. There's less and less particles that are moving really slow. There's more and more particles that are moving really, really fast. But there's always some really slow particles and some really fast particles. And that's kind of what the Maxwell-Boltzmann distribution is meant to show us. The reason why these curves keep getting shorter is that we're trying to talk about one sample of a gas with this graph. So if the number of particles aren't changing, as the curve moves to the right, it also has to get flatter so that the total number of particles it represents staying the same. If you think about the area under each of these curves would be about identical. And that's why they when they move to the right, they also get lower to keep the number of particles represented the same. And that's sort of your introduction to states of matter, the units that we're going to use when we talk about the gas laws, some phase changes and how temperatures change and how stored energy changes during phase changes. That boiling is a little more complicated than your average change of state because it depends on the pressure of the atmosphere around it, and some assumptions about how gases are going to behave that we're going to call ideal behavior.